TCP/IP model, application layer. The application layer is the topmost layer of the TCP/IP model. It's where apps and network services meet. But here's something important. The application layer does not include the actual applications like web browsers, email clients, or chat apps. Instead, it provides the rules and services that these apps need to communicate over the internet. Let's say you want to visit a website. Your browser doesn't just magically pull the page from the internet. Instead, it uses HTTP, Hypertext Transfer Protocol, a set of rules that tells web servers and browsers how to talk to each other. When you type a website's address, your browser sends an HTTP request to the web server asking for the home page. The server replies with an HTTP response, sending the web page data back to your browser. Your browser then displays the page. Without HTTP, web browsers wouldn't know how to ask for websites. The application layer includes many protocols that help different types of software communicate. Here are some key examples. HTTP, HTTPS, helps browsers load websites securely. SMTP, POP3, IMAP, used for sending and receiving emails. DNS, Domain Name System, translates website names, like google.com, into IP addresses. FTP, File Transfer Protocol, transfers files between computers. Don't worry, we'll get more familiar with these protocols as we go along and use them in different parts of the course. Think of the application layer as a bridge. On one side, you have applications like browsers, email clients, and file sharing tools. On the other side, you have the internet and networks. The application layer's job is to ensure these applications can use the network efficiently, without needing to know the details of how data moves. So next time you browse a website, send an email, or download a file, remember, it's the application layer making it all possible. Transport layer. The transport layer is the second layer in the TCP/IP model. It provides services to application layer protocols by ensuring data delivery between devices. The two most common transport layer protocols are TCP, Transmission Control Protocol, ensures reliable, ordered delivery. UDP, User Datagram Protocol, sends data quickly but without error checking. Different applications use different transport protocols based on their needs. For example, web browsing and emails use TCP for reliability. Live video streaming or gaming use UDP for speed. One of TCP's most important services is error recovery, ensuring data arrives complete and in the right order. Imagine you request a web page from a server. What if part of the data gets lost in transit? Without a recovery system, the page wouldn't load correctly. That's why TCP has a built-in system to detect missing data and resend it. Let's break it down step by step. Before sending data, TCP breaks large chunks of data into smaller pieces called segments. This makes transmission more efficient and allows TCP to manage lost or corrupted data more easily. Each segment gets a unique sequence number in its header. This helps the receiver identify the order of the segments and detect if any are missing during transmission. Without sequence numbers, the receiver wouldn't know how to put the data back together properly. When the receiver gets a segment, it sends back an acknowledgement to confirm successful delivery. If the sender doesn't receive an acknowledgement for a specific segment, it assumes the segment was lost and needs to be resent. If a segment gets lost or corrupted during transmission, the receiver notices a gap in the sequence numbers. For example, if segment 1 and 3 arrive, but segment 2 is missing, TCP recognizes the issue and requests a retransmission. The receiver's TCP sends a request to the sender asking for the missing segment to be resent. The sender then resends only the missing data, ensuring efficiency without retransmitting everything. Once all segments arrive, TCP reorders them based on sequence numbers and hands over the complete data to the application, such as a web browser, email client, or file transfer program. Now, here's a question for you. How does TCP know which application the received data belongs to? Drop your answers in the comments. Network layer. The network layer is the third layer of the TCP/IP model. Its job is to find the best path for data to travel from one device to another across a network. The key responsibilities of the network layer are assigning unique IP addresses to devices, finding the best path for data to travel, moving data from one network to another. The Internet Protocol, IP, is the core protocol of this layer, which is why TCP/IP is named after it. Imagine you just wrote two letters, one to a friend across town and another to a friend on the other side of the country. You put both in envelopes, add stamps, and drop them in the mailbox. For you, it's simple. You don't need to think about what happens next. You just trust that both letters will get delivered. But for the Postal Service, things are a bit more complicated. The letter going across town? That one might just get put on a local truck and delivered the same day. The one going across the country? That's a different story. It will pass through multiple post offices, maybe a sorting facility, even get loaded onto a plane before it finally reaches your friend. Just like every house or office has a unique address, every device connected to a network has an IP address. These addresses help data reach the correct destination, just like postal addresses. But instead of post offices, we have routers in the network. Routers are responsible for forwarding packets to their destination using the best possible path. When a server receives a request from a client, it prepares the data to be sent across the network. The application layer sends the data to the transport layer. The transport layer adds a TCP header, including something like sequence number 1, and passes the data down to the network layer. Just like a letter needs both a sender and a receiver address, the network layer adds the source and destination IP addresses to the packet. In this case, the source IP is 1.1.1.1, which belongs to the server, and the destination IP is 2.2.2.2, which belongs to the client. But here's a question. If we already have the destination address, why do we need the source address? Think about it and drop your answer in the comments. The server doesn't worry about the best route. It simply sends the packet to the nearest router, which is R1, just like dropping a letter into a mailbox and letting the postal service take over. Router R1 receives the packet and checks the destination IP address, which is 2.2.2.2, and looks for the best path to send it. R1 has two options, R2 and R3. Based on certain factors which we'll talk about later in the course, it decides to forward the packet to R2. Router R2 receives the packet and does the same thing. It checks the destination, finds the best next hop, and forwards the packet toward the client. Eventually, the packet reaches the client's device. It gets reassembled and the web page loads. This entire process is called IP routing. It's how data moves across networks quickly and correctly. As we go through this course, We'll explore routing in much more detail, how routers make these decisions, and what rules they follow. But for now, just having a clear picture of the basic flow is a great start. All right, let's move on to the last layer. Access layer. We've talked about how data travels across networks and how routers guide it using IP addresses. But there's one more thing we need to understand: how the data actually moves across the physical connection. That's where the access layer comes in. In the TCP/IP model, the access layer includes the data link layer and the physical layer. These two layers work closely together to get the data from one device to another over the actual network cables or wireless signals. Let's start with the physical layer. This layer is all about the hardware. It defines things like cables, connectors, and the actual signals, like electricity or light, that carry data from one device to another. But physical signals alone aren't enough. We need some rules for how to send and receive those signals. That's where the data link layer comes in. The data link layer makes sure that devices on the same local network can talk to each other. It adds something called a header and a trailer to the frame for helping make sure the data arrives to the next device correctly. I know, it sounds a bit confusing. So let me explain it with a quick example. Imagine a server needs to send a packet to a client. But the server isn't directly connected to the client. It has to send the packet through other devices along the way. In our example, the packet first goes to router R1, then to router R2, and finally reaches the client. This journey from one device to another before reaching the final destination is handled by the data link layer and the physical layer. These layers are responsible for moving the packet one hop at a time, making sure it gets from the server to R1, from R1 to R2, and then from R2 to the client. The server checks its physical connection to router R1. Based on the type of connection, whether it's a wired Ethernet cable, a fiber link, or a wireless signal, it adds a header and trailer to the packet. These are used only for sending the packet to R1 and won't be used beyond that point. When R1 receives the packet, it removes the header and trailer that the server added. Then it checks where the packet needs to go next. In this case, the next hop toward the client is R2. So R1 adds a new header and trailer based on its physical connection to R2 and sends the packet forward. The same thing happens again at R2. It removes the header and trailer added by R1, adds a new one based on how it's physically connected to the client, maybe over Wi-Fi, and then sends the packet to the client. As you just saw, the header and trailer changed at each device during the journey. But here's an important point. The transport and network layer headers, like TCP and IP, stay the same the whole way through. Never forget that. It's one of the key points when it comes to how packet forwarding works. TCP/IP summary. As we saw from the beginning of this video, each layer in the TCP/IP model adds its own piece of information to the data. That's usually a header, and sometimes a trailer. It's kind of like putting a letter in an envelope and writing the address on it. This whole process is called data encapsulation. At the application layer, we prepare the data and add some extra information, like an HTTP OK message, before sending it down to the next layer. At the transport layer, we add a TCP header to help with reliability. At this point, we call the data a segment. Then we move to the network layer, where we add source and destination IP addresses to the segment. This creates what we now call a packet. Finally, we reach the access layer, where we add a header and trailer, turning the packet into a frame. This frame is what actually gets sent across the physical medium, like a cable or Wi-Fi. That's how encapsulation works, each layer wrapping the data to prepare it for the journey. Now let's talk about what happens at the destination. When the frame arrives at the receiving device, the process is reversed. This is called decapsulation. The access layer removes the header and trailer and passes the packet to the network layer. The network layer checks and removes the IP header, then sends the remaining segment to the transport layer. The transport layer removes the TCP header and finally passes the data to the correct application. So usually, the sender does the encapsulation, starting from the top layer and going down, and the receiver does the decapsulation, starting from the bottom layer and moving up. But here's a question. Is there any device that does both encapsulation and decapsulation? Yes, you got it. Routers in the middle of the path do exactly that. They receive a frame, decapsulate it, and then encapsulate it again with new headers and trailers before sending it to the next hop. So that's it for this part of the TCP/IP journey. If you found this helpful, go ahead and like the video and subscribe to the channel. It really helps me keep making more. And if you've got a question or just want to say hi, drop a comment. I'll be checking and replying. Thanks for watching, and I'll see you in the next one.